So let's get started. Today's topic on our lecture is personalization and recommender systems. So, personalization is a quite a loaded term, and a lot of companies currently, actually doing it or discussing it. And it's probably worth spending some time understanding what we understand by personalization. And personalization is delivering the right experience to the right customer at the right time, right? And as a customer, you kind of understand when the services that are being delivered to you or the product that being delivered to you, they're personalized, right? Because whether it is an advertisement, an ad that being showed to you, or it is the discount that you were given by email that is, for example, very different from discount somebody else would get, or the way the airline treats you on the flight because of your habits and frequent flyer miles. So the right experience really means providing precise marketing service that the person can be interested in, content that is designed for a particular person in mind, providing additional rewards, products and recommendations. And in fact, this whole sort of personalization concept started big time from digital native companies like Amazon, Netflix, that provided us with personalized recommendations for books, for purchasing, and in Russia it's Ozon that doing it, and Netflix, of course, recommendation for shows and movies. So the second part is, so first it's the right experience, right? So what sort of the company can do for you. The second is through the right channel, right? Whether it is email, mobile, through the web, through the push notifications, through the call center, or maybe, when you are, for example, in the restaurant. So that's actually also very important because, say, for example, for me, calls are useless. I will not pick up the phone if I don't know the number, but some say push notifications can reach me. And providing this experience in the right time. So when I am interested in like advertising coffee, when I'm far away from say Starbucks, doesn't make sense. It's going to only annoy me. But if I am somewhere around the corner, why not? Depending on the weather, for example, giving discounts, if it's cold outside, giving discount on iced drinks also kind of doesn't make sense. So you need to take that into account. And time of the day, frequency, and even sequence of, for example, offers, that all might matter. So again, personalization, it's really about the personalized, the tailored experience to the customer, delivered through the right channel at the right time. I'm going to put on a little bit of consulting hat for a second. This, BCG together with Google did some, asked people about the experience from personalization, with the goal to understand how much personalization actually affects the results, right? And here, that's the result of questionnaires and of survey, and there were a bunch of questions asked. But what we have here is just some simple questions. For example, what you see on the x-axis, horizontal axis, is level of personalization experience at a particular retailer, and that has to do with retailers, with no personalization to very high personalization at the retailer. And the results of the survey shows that when the retailer provides a good, precise personalization service, a customer stands to buy more items than they originally planned in the store. And the uplift there is 110%, right, compared to no personalization. The value of average order also increases by 40%, and net promoter scores. So this is, you know, how, if you're going to talk about that you experience other people, also grow. So these are sort of survey experiences, survey results, but there are also, of course, you know, hardcore numbers that coming from the stores that implemented. And, you know, from the traditional industry, most noticeable personalization services, they are, say, in travel industry, you know, it can be hotels, it can be, you know, airlines that try to personalize your experience. You know, Starbucks is a very well-known example of personalization. In fact, the fact they're even asking your name, I mean, that's kind of one of those things, but they're really using the information they collect about you to offer certain type of discounts. So in order for personalization to work, you actually need a lot of components. And in fact, you know, the personalization was not, you know, broadly discussed simply because previously it was very hard to do. It was very hard to do because it has to be based on certain metrics and measures, so data that should be collected about customers. Then the data should be in a certain way managed, right? And think about, again, Starbucks example, you know, they have stores, you know, around the world, I think like in 80 countries around the world. So you need to manage, to be able to manage all the data being collected. And I think they have around 15 million, you know, loyalty program customers. So that's huge data sets. So then the analytics engine should be created, those that allows us to generate those personalized offers, right? Select the right products to recommend. And then there should be, of course, you know, a delivery layer, which is now mostly through mobile phones, but can also be done in person whenever you're visiting, for example, a store or coffee shop. So there is this lot of blocks that should be in place in order to create sort of working personalization program. And not every company today still have it, but those that have can, you know, greatly benefit from it. And it is, in some sense, sort of a loop, because providing personalization, you're also collecting customer feedback on this personalization, that feeds back into the system and allows the system to make better predictions, better recommendations about what customer wants. So that's sort of overall the personalization aspects. And we're going to talk about today about this part, the analytics, where is it? The analytics engine part, right? So what we can create on the back end in order to make experience more personalized. And we'll be focusing on retail or on examples from, in this case, the examples will be also from coffee shops. Okay. So we'll start with one technique, which is actually sort of precedes this whole discussion on personalization. And it's called market basket analysis. And you'll later on realize how it is connected to the recommendation systems we're going to talk about a little bit later. So the idea of market basket analysis is to try to identify and find sort of the strengths of the association between pairs of products purchased together. Now, for the store, for consumer goods, for the stores, for example, it can be products. If you think about, say, I don't know, banking, that can be banking products, you know, hotels, some other travel products that people usually purchase together. And so the idea is to build those type of rules that says if A, then B, right? Sort of if customer does this, then he will also do this. If customer buys this, he will also buy that product. And that can be used, first of all, for cross-selling of the items, right? Sort of offering items to the customer. It's also used a lot for product store placement, where you position products next to each other. For example, you go to the store, you often will see like chips placed next to the beer, which is sort of obvious association, but there are many more non-obvious, right? Then the idea of affinity promotions, which is promotions that will actually promote either, depending on what's decided, either both items that associates with each other, or sort of one or another, right? Because you can actually understand if one item is substitute for another. So, and there are sort of a bunch of other usages that are available. Now, this is not yet a personalized experience, right? We're not going to be talking about here about the customer. We're going to be talking about similarity between products and services. Later on, we'll map it onto how to use it with a customer to actually provide personalized experience. So the typical data that being collected and that's needed for this type of approach is what's called point of sale data. So this is the data that is collected, the cash register, and that's usually transactions. And what's important is to have sort of the transaction ID and make sure that items that are bought in the single purchase are shown. And here, for example, and this is, by the way, the data you'll be working on in the homework, you can see a few transactions, and I highlighted in yellow, for example, 2 transactions in the same store number. And if you look here in the item family name information, there is latte and muffin, right? And so you can actually create from this, you can create rules saying that latte and muffin usually purchased together. Now, you will create this if you find this type of occurrence like many times. And we're going to talk about it in a second, how to actually define that many times. Now, when you do this market basket analysis, you don't care about customer, in the sense you don't care about particular customer who made that purchase, right? You're actually looking only at the basket. The data that we're providing, you actually have some card numbers, some IDs here. These can be used later on when we try to do personalization, right? But for the market basket analysis, you don't need card numbers. So this is a kind of heavy loaded slide. We'll go slow through this, but it is the essence of association rules. So let's try to understand what we have here and go slowly. So first of all, here is the transaction data, right? So it's similar to what we just looked at, just a bunch of transactions. And the way it is shown is there is transaction ID, and then there are items that has been purchased in that transaction. Let's say, the first transaction has a basket had milk and bread. Then, for example, this transaction number 4 purchased 3 items. Then transaction number 3 purchased those 2 items. So that's, the data you normally get. And so what we want is we want to be able to generate the rules given by this implication, if X, then Y. For example, I want to build a rule and see how much it's confirmed by our data. Rule, for example, if butter and bread is purchased, then milk will be purchased, right? Now, let's try to look at this data and see if this rule makes sense. We're not going to talk right now on like how I came up with this. We'll discuss it on the next slide the ways to generate these association rules. But right now, let's see how to make sure those association rules are actually make sense, right? And there are several metrics that has been developed to measure the quality of association rules. So the first metric is called support, right? Support for a rule. And support is just a frequency of this item set or this particular item in the data. So if support is 0, it means this combination of items never occur, right? So for example, if I take just an item which is butter, butter has been purchased twice out of 5 transactions. So support is 0.4, or other way is, it's 40%, sort of 40% of transactions actually has butter. So in other way to think about this, the probability to purchase that the customer will purchase butter is 40%. Now, if I look at the combination milk and bread, in this data set, and milk and bread, they both, those combinations, right, happens twice. So again, it's 40%, right? So the support is 40%. Now, the combination milk, bread, and butter actually happens only once out of 5 transactions. So the probability that you get that combination is 20%, 0.2. So that's support. The second metric that is useful is called confidence. And confidence tells us, if we select a particular rule, how often this rule is actually followed in the data. So how often this rule is true in the data. For example, we created a rule that says if milk and bread is purchased, then butter will be purchased, okay? How to calculate this confidence level? Well, the formula gives us this expression. It's support for the milk and bread divided by support of the butter. But if we can follow the definition, or we can actually look at the description. So how often the rule is true in the data? So this rule actually happens only once, right? So right, this rules so from this rule happened only once, because when the milk and bread, right, happened when the butter was purchased. At the same time, we realized that there is also another occasion when milk and bread has been purchased, but butter was not purchased. So there are 2 situations when milk and bread was purchased. In one scenario, butter was also purchased. In the other, it was not. And so that means the confidence in this rule is actually 50%, because out of 2 occasions when sort of X were present, Y was present only once. You can also think about this from the point of view of probability, that in fact, support is just the probability of event, right, as we just discussed. So the confidence is really the ratio of the probability of those 2 events happening divided, normalized by probability of the first event. And that gives us a conditional probability by the rules of probability. Conditional probability means what's the probability of Y if X is happened. And so in this case, X is milk and bread, purchasing milk and bread. Y is purchasing of butter. So we know that this happens. So the question, what's the probability that butter will be purchased? Well, there are 2 outcomes, either it's going to be purchased or not. And from our data, it follows that this probability is 50%. Let me pause here for a second. Does this make sense?
Yes.
All right, any questions, guys? All right, we have 29 people. No questions, okay. So the last thing is, and probably sort of very important metric here is lift. And lift actually tells us how the presence of one item actually affects another, right? So what I'm trying to say is that I try to compare, and again, I like to look at the probabilities. You can look this definition through the support, or we can right away write it through probabilities. It's the probabilities of both events together, X and Y, divided by the probability of X times probability of Y. Now, if you remember a little bit from the probability theory, if two events are independent, truly independent, then P of XY can be factored out as a P of X times P of Y. And then it will cancel out with denominator, and the lift is going to be 1. So if two events are independent, lift is equal to 1, so no lift happens. But it can be greater than 1 or less than 1. And when it is greater than 1, it really means that the presence of the one of the items affects the purchase of another. If it is less, then it means it's actually by the presence of one item, you decrease the probability of purchasing of another. And in this sense, by the way, in that case, it can be like substitute items, right? If you buy this, you don't buy that. So these are substitute items. So let me show you an example. Again, we're looking at this rule, milk, bread, then butter, right? Let me clear all my drawings. So we're looking at this rule from milk and bread. What's the lift in terms of purchasing butter? Well, we're gonna put support for X and Y. I'm sorry, support for milk and bread. And support for milk and bread is a probability that they purchase together, right? And milk and bread purchase together twice out of 5 transactions. So the probability is 0.2, right? It's oops. I'm sorry, I put it in the wrong place. Let me try it again. So we need to calculate, if you notice what we're doing here, we need to calculate support, right? For both X and Y. In our case, X is milk and bread. This is X. And Y is butter. And so we're trying to calculate the probability that X and Y happens together, right? And let's see when events X and Y happens together. Events X and Y happens together when the customer purchases milk, bread, and butter, right? That those events X and Y happens together. So this is the case when that happens, right? Now, what we're normalizing with respect to is probability of X and probability of Y. Now, probability of X is when only milk and bread are purchased, and that's 1 and 2. And probability of event Y is when butter is purchased, 1 and 2, okay? And so that's how we compute those things. Now, the big question that remains is, okay, I came up with this rule. I just said, like, look, here is a rule. Here we can calculate here confidence and we can calculate lift for the given rule. And so it can tell us whether this rule is, again, if we're confident in this rule, which means, you know, if this rule occurs a lot, and lift if, you know, this, within this rule, if this rule sort of makes any sense, if it is interesting or not, right? Lift meaning, you know, interesting part of the rule, if purchasing of one item affects another, and if it affects like sort of lifting the probability of purchase of another or dropping it. So lift, it is how interesting the rule is, and confidence is how confident we are in this rule, so how often it actually happens out there. So that gives us the opportunity to evaluate the rules. But how do we come up with the rules? And there is a way to do it. In fact, there is an algorithm, a very famous algorithm. It's called a priori algorithm. And now we're getting to the sort of territory of more recent algorithms that even have, you know, we even have authors for these algorithms. And we're gonna go quickly through this algorithm. There is some sort of details that are quite interesting if you go in depth, but I want to explain to you like the main concept of the algorithm. So let's say we again have, you know, the database of transactions. It's transaction ID, so some transactions, and there are some items. This time it's, you know, items that has been purchased in the transactions. So, you know, the way this algorithm is built is the following. We really don't need or don't want rules that have small support, right? Because small support means, you know, it doesn't occur very often. So this is not an, you know, it's not, and it cannot be an interesting rule. It's not an interesting combination. Now, confidence will be later on how confident we're in this particular rule. But first of all, we should have quite a few situations when this rule, when this combination of items, sorry, not rule, but a combination of items actually occurs, right? If it happens only 1 or 2 times, you know, kind of not interesting, right? And that's why, by the way, association rules, this is really system designed for popular items, right? Popular items, like lots of frequent purchased items. So what does algorithm do? It starts with the transactional database and then does like the very, very first scan through this database and just calculate the frequency of every item, how many times this item has been purchased, right? So we just calculate the frequency of every item, which is, if we divide by the total number of transactions, which gives us the support, right? And you know, for example, item A has been purchased 2 times, item E has been purchased 3 times, and so on. And then what we can do is we can, for example, threshold it on a support level, right? And let's say we want the support for our items. I didn't write it. We want the support, and we'll have it sort of unnormalized, right? Support be greater or equal than 2. So item D that happened only once, we throw away. Okay. So the next step, so we got this item set. Then what we're gonna do is we're gonna form all possible pairs of the items, right? And that's gonna be, for out of these items is gonna be A, B, A, C, A, E, B, C, B, etc. And then we're gonna go and check how often those pairs actually occur within, those combinations occur within our database. So for example, A and B occurred once, and the support here is 1. AC occurs here in this transaction and in this transaction. say BE happened here, they'll be purchased together. Where else? Here and here, 3 times. So it's an interesting combination. So we keep it. All right, then we filter out and we keep those combinations. Then we expand the set, again, go for all the possible combinations of 3 items. Look at them, check that they are available in, subsets available in the previous set, and calculate the thresholds. And we realize that the combination of B, C, and E is the only one that survives with support 2. It is this combination where, let me clean it. That existed. So what have we obtained? What we have achieved? Well, we created several level of interesting combinations. So for example, here is a bunch of combinations of support 2 and 3. And probably the most interesting is this one because it has the biggest support. And then there is another combination that exists here out of 3 items with support greater than we threshold on. And so now we have those combinations. And from those combinations, you can build the association rules we talked about. You can look at the rules, for example, given A, calculate lift and confidence that from A, when purchased A, the customer will purchase C. Create the rule goes sort of going backwards from C to A. Create the rule BC purchase E, and verify both confidence and lift for those rules. And then out of that, you select the most sort of interesting rules. Now, in practice, what we often observe is that there are some rules that come up out of this that are, kind of trivial, right? Trivial rule like, bread and butter, yeah, people do buy together, or beer and chips, they buy together. Sometimes you also come up with rules that are sort of weird and useless. And, in fact, this is sort of famous in literature. If you look up this beer and diapers, when researchers ran some experiments, they found that beer diapers has been purchased together, and then they came up with a lot of, theory why it actually happens. But later on, it was not confirmed on sort of many other data sets. So there are some rules that are actionable, others are not, and that's already up to business analysts to decide whether a particular rule can be used, to either offer to the client or as a combinational purchase, or to use it for store allocation of the products. Now, Amazon uses this automatically, right? It's probably there is certain threshold that are positioned there to make sure the rules have, quite strong lift and high confidence. So that's association rules, right? These are not, exactly personalization, but this is a way to find out the product substitutes, right? Product replacements. This is a way to, help sort of positioning products in the store, and also if you're shopping online, that's a way to show your other products while you're buying one of them, right? So that's like sort of classic, goes back to 1995, and really a lot of retail using it, right? This is sort of the workhorse. Now from that, we're going to be switching to the actual recommendation systems, right? Before we go there, any questions?
Okay, yes, I have a question. May I ask it?
Yes, yes, please.
Okay, so you said that this algorithm is used by several different huge companies, and I just cannot understand how we can process the huge amount of data by using this algorithm. I mean, the complexity of the resulting combinations of all items is factorial, and so I don't know, in the real life, it seems to me that it would be just kind of
Yeah,
impossible to calculate it. So yeah.
it's a very good question. You're absolutely correct. If you actually just try to build out all the possible combinations, right? Sort of like, okay, you have products, then you build all pairs, then you build all triples, then you build all, 4, 5, etc., etc. There is no way to do it. You're absolutely correct. It's factorial large. Now, the way it is actually, the only reason it works is because of this a priori algorithm. If you notice, with trimming really, really fast, we're trimming our options, right? We're cutting out we're cutting out those combinations that occur infrequently. And notice, I put here pretty low threshold. I put here support 2, but I can put support here equal to 3. For example, instantly, we get only 3 combinations out of 5. And so if you have 10,000 items, you control that level of support, that level of frequency, and that allows you to prevent this sort of factorial explosion. And by the way, it's frequent item sets. It's even in the name, so it's only focuses on frequent items. It's not going to work to find sort of infrequent or infrequent pairs, right? So it's not a sort of a discovery of some novelty. It is something that is very frequent, and by cutting out, we reduce this factorial large, because again, like you're absolutely correct, this tree of combination grows really fast, and by selecting only very frequent items and very frequent pairs, and on every step, if you notice here, we are we're cutting, right? Here we are reducing, here we again reduce the set. So because of this reduction every time on the frequency, we prevent it from sort of combinatorial explosion.
Okay, thank you. Now I understand.
Yep.
Thank you.
Okay. And on top of it, there are actually quite a few very efficient ways to do this in a large database. At the end of the lecture, I recommend you a book if you're interested to actually how it's implemented. There are a lot of sort of ways to make it work on large data sets. Okay, good. So let's move on. So the true personalization, of course, comes from recommendation system, and today probably the most well-known and sort of worldwide known companies that do recommendation, that have very powerful recommendation engines, are Amazon, that so they started with books, and now of course they do recommendations on everything, and Netflix, for example, where they have really, really good recommendation system for movies. Obviously, like Spotify does recommendations, Facebook does recommendations by, providing you some, news articles to read. LinkedIn or friends, LinkedIn does recommendations, sort of friend recommendation. Google, YouTube, recommending videos. So a lot of companies are actually doing it. All the digital natives are doing it. And we want to learn a little bit more how it's done. And nowadays, like classic brick and mortar stores are also started using it, right? And not only on their online properties, but sort of in store. By the way, if you think about the recommender systems in Russia, guys, who has the best recommender systems? Which company?
Yandex.Zen.
Yandex.Zen?
Or Yandex Music, I think. Really good recommendations for me.
Yandex Music, okay. Yeah, actually, I don't know precisely what algorithm they use in there. We're going to talk today about some sort of, some basic algorithm, like sort of the mother of all algorithms in recommendation systems. I will also touch upon some more modern algorithms, but honestly, since probably the year 2000, when there's algorithm things, the recommender things started, we got confidence in recommender systems, and there are a lot of people who are actually working on it as research scientific projects, and it became part of machine learning. One thing which I want to mention, and that's also I think very interesting, is why recommender system, why nobody bothered before. The reason is in this Pareto curve, right? And you, of course, familiar with this. It's has multiple names. It's a power law. It's 80-20 principle, etc., etc. But the idea is very simple for us. The idea is that you have some products that are extremely popular, right? And extremely popular means the volume of sales for those products are pretty high. And these are the products that traditional stores like to have. Because, for traditional store, having a product, actually there is, you pay costs. Well, first of all, you put money into it, you pay costs for storage, you pay costs for delivery, you pay costs for, it takes shelf space. So there are a lot of things that comes together with having a product on a shelf in the store, and putting something on the shelf that is not popular, it's quite often economically just impossible, right? And so traditional stores are focusing on popular products, and that's why if you're looking for something exotic, it's actually pretty hard to buy in traditional store. At the same time, when online came, and all of a sudden you don't need to put products on the shelves, and you can actually have huge warehouses, that's where Amazon operates, right? On this long tail, which is products that are quite unique and maybe purchased once a month, but they're still purchased. And this tail is very, very long. And Amazon, by shipping it, right, is avoiding all the costs associated with storing it, bringing it, blah, blah, blah. And so it makes it profitable. Now, what's interesting is, again, traditionally people were looking at this as like, okay, yeah, this is a popularity, sort of times the volume of sale, that's where money is. Well, in fact, this tail is very long, and total money, total revenue you make on online versus say offline, or this rare products versus popular products, is really this area under the curve. And if tail is very long, this area can actually be even bigger than this one, right? And so if you think about music recommendations, this is all your these are like sort of movies and music like blockbusters, and this is your indie and like endless other, the musicians. Or the problem here is with a store, you have shelves, customer comes, sees the product on the shelves. Here, with all these products, what's missing is a discovery process, right? If the customer knows precisely what he wants, he can find it with a search engine. But if he doesn't know and he wants just to browse, browsing this tail is impossible, right? And so that's where recommendation systems come in, and that's why they became very important and very popular precisely within the online industry, right? So now that technology is started being used in offline, and that's what we're going to talk about. But Amazon was like literally the first one who put this into like real commercial and scalable system. So in fact, I'm showing here the paper published by Amazon engineers. It is year 2003, Amazon.com recommendations, item-to-item collaborative filtering, which kind of literally sort of jump-started interest in recommender systems, and companies started implementing them. I would say first papers on the recommendation systems were published in like late 90s, but they're mostly academic interest. And this kind of was a very big push. Now, speaking of recommender systems, sort of broadly speaking, there are really sort of two types of systems. One type is what's called collaborative filtering. Now, the idea here is that you're actually trying to make recommendations based on the sort of collaboration, right? So the idea is that you're looking for similar users and then trying to offer to a customer what users like the customer would buy. And the way it works, you're not looking at some sort of customer properties like gender, age, or some other information, but you do look at the customer purchases. And so this is the system that's entirely sort of closed in the sense it does not require external information, and it is literally information or context agnostic in the sense that it's equally applicable to movies, to grocery products, to mix of movies and grocery products. It doesn't matter. As long as you use transactions, that's the only information that's required here. And we're going to talk about that. So the other way, the other approach is content-based, and it's filtering. It shouldn't be here. It's just content-based recommendation engine. It is where you understand the content, and you can, for example, say, okay, this is a movie. This is a say action movie based on spy novel with some famous actors. And so let's see what others, action movies with the same actor or director out there of the same genre, and then recommend them. So that's content-based, right? You're digging into the content. That is much more expensive to do. This will be very, very domain-specific, and surprisingly, it doesn't work as well as collaborative filtering. So collaborative filtering is sort of very simple and amazingly efficient and effective idea. Now, of course, there are methods that combine those two things, right? There is a sort of hybrid methods of where you use collaborative filtering, and on top of that, you add a bit of content. And within collaborative filtering, there are an entire set of algorithms how you can actually do that. So let's look at a few of them. So first, the first idea that we need to kind of understand is the following. You can easily represent the transactions, the purchasing, and here, oh, and by the way, here is where user ID is important. And so collaborative filtering works for users that are logged in and registered on the website, or users that have loyalty card or some part of some loyalty programs in the store, so you can identify users. Okay, so let's say we have a bunch of users and they are purchasing some items, right? In this case, books. So there is a particular structure that we can actually build out of those transactions, and that's called a bipartite graph. It's a graph that has two types of nodes. One type of nodes are users, and another type of nodes are items, those books. And so what we have is user A purchased book A, purchased book 1, purchased book 2, purchased book 3. User B purchased book 1, book 2, book 3. User C purchased only book 3. Make sense? Okay. And now, interesting part. From that bipartite graph, we can actually create what's called projections. And it is sort of user projection graph and items projection graph. So the idea is very simple. Let's pick up only users, and let's connect only those users who purchased the same items. For example, user A and user B both purchased book number 1. So let's connect them. User A and user C both purchased book number 3. Okay, so let's connect them. But we can do better than that. In fact, user A and user B both purchased book 1, book 2, and actually book 3. So they have 3 books in common that they purchased. So we can put a weight here. All right. And by doing that, we can build a similarity graph where the nodes are users and the weights on the edge corresponds to how many items in common they have purchased. And by looking at this, you can easily see that without even knowing what the heck items are, whether it's books or alcohol, but the users A and B probably have similar tastes because they purchased 3 items that are the same. All right, guys, pause here. Does this make sense?
Yes.
All right. So, so we can build on this user projection graph or user similarity graph. The same way we can actually deal with, we can build what's called item graph or item projection graph following exactly the same approach. We can say, okay, item 1 and item 4. Let's see. Oh, there is this user B that purchased them, both of them. Okay, let's connect it. Item 4 and item 3. Oh, interesting. Item 4 and item 3. All right. Item 4 and item 3, they're connected. I don't know why they're not connected here. So they should be connected. Then item 1 and item 3. Let's see if it is connected through the user B and it is connected through user A. So they're connected through 2 users. So we can put here 2. So the idea is that, again, you say 2 items are connected if they've been purchased by the same user. Not necessarily in the same transaction, the way we did it in market basket analysis and association rules. We don't care about them being purchased in one transaction or in many transactions. Doesn't matter. It just says that the users, that it's the same user that purchased both of them, maybe in the different moment of time, maybe in the different transactions. And if there are many users that purchase those 2 items together, you know, maybe they're similar. All right, so these are the logics. And based on those graphs, you can actually create a recommender system. How would you do this? Well, let's look at the first approach, which is user-based recommender system. So what we do is, remember, we have this user graph. So if I pick up one user, and we have this, oops, let me try it here. So we have this user similarity graph. And so for every user, we can pick up other users similar to this user. So what do? We pick up a user for who we want to make recommendations. The next step, we'll pick up users similar to that user based on our graph. And of course, there might be a lot of users similar to our user. We can sort of threshold it at some level, okay? So we pick up similar users. Now, for each of those similar users, we do have their baskets, or I mean, what they purchased overall, their purchasing history. This is what the first user purchased, the other user purchased that, the third user purchased that. Then what we do is we join those lists. We merge them, and then we count how many times each of the items occurs there. So, and then we rank by that. So the polo has, 4 times occurred, gloves 3 times, sneakers twice, socks 1. And then this is what you recommend to this user. That's it. That's collaborative filtering, user-based top-end recommendation algorithm. Very simple, works like a charm. Make sense? Okay. Please stop me if there are questions here.
I have a question.
Yes.
Yeah, here we are kind of seeing the theoretical part, but in practical business, somehow, I don't know, because here you are recommending someone to buy these things, but sometimes you also make a discount, let's say, right?
Oh, okay. Yeah, this is more, yes, this one does not have discounts. So typically they're actually, you know, you know, in the real scenario, you actually have a bunch of algorithms that are working, right? One algorithm is this recommendation algorithm, which actually recommends or generates those candidates, right? We are literally generating candidates items to recommend. But then, you know, again, in the sort of the simplest scenario, we just go ahead and recommend it. In more advanced sort of real life settings, there will be another algorithm that will calculate the propensity of a particular customer to buy a particular item, right? So
Yes.
for that algorithm to go through all the possible items in your catalog is impossible, but it can easily calculate that propensity for a particular customer. Then you might have an algorithm that for a particular customer cluster, it will know price sensitivity. And so it might know if the customer more likely to buy if you drop the price. And based on all that, you can actually calculate which item you want to show.
Mm-hmm. Okay. So, but it's real. I mean, these kind of complex systems are running today.
Oh, absolutely.
Yeah.
Yeah, absolutely. They're actually running since 2003. So I've been running for 20 years now. Okay, so that was a sort of user-based algorithm, right? Now, of course, you know, researchers measuring the algorithm quality. There is a different approach. As I said, there is this item-based approach. And let me go quickly through that one. It's sort of symmetric to what we just discussed. So the idea is that we have a user, and now we start by the items that this user purchased. All right, so this user purchased gloves and a t-shirt. And now we're not looking for other users like this guy, but we're looking for similar items. Remember, here we created the item similarity graph. So, oops. Item similarity. So we're going to use it now in here by looking up the most similar items from that graph to the t-shirt. And these are the most similar items. And then the most similar items to gloves. These are the most similar items. Then the same thing, we merge them. And for example, we can rank them by similarity because the graph contains similarity. So we can use this to rank them and offer to user A. So that's called item-based collaborative filtering. And in fact, this one, you know, works better than the user-based collaborative filtering. It's just sort of fact of life. So these are two algorithms. When somebody says collaborative filtering, that's what they mean. These are like two algorithms, sort of item or user. But the thing is, in both cases, these algorithms are based on the transaction, on the history of purchasing, nothing else. They're not actually looking into the content. Now, in fact, if you notice, we're just looking into the sort of binary scenario, buy, not buy, right? You can also extend this approach to ratings or ranking. If you think about, well, not maybe Amazon, but more of Netflix or Yandex Music or any other Spotify music, you often rank items, right? It's not that you bought, but you listen, you like, you didn't like, right? You rank from 1 to 5. And so instead of those purchase graph, you have a ranking. Now, you can also show it as a graph. That's absolutely fine. But there is another approach which look at it as a matrix. And so matrix here is really just a table where, you know, on one axis there are users, on the other axis are items, and here is actually just sort of books. By the way, actually pretty good books here. You know, users can rank books, right? You read, you rank. It can also be represented by a graph where you connect the first user, you know, with the first book, and the first user with the second book, and the first user to this book, and you put here weights on edges, right? So it is also this bipartite type of a graph, as we saw previously right here, but now on every edge of this graph, there is a weight, which is a rating. And you can represent those ratings as a network, or you can represent it as a matrix, okay? And empty spots means user never looked in there. So what you can actually do based on this matrix is to build the same, as we discussed before, similarity graphs or similarity matrix, where we calculate how similar are users based on their ratings, or how similar are items based on user ratings. So it's exactly done the way we did before with the graphs. Now, the only difference is that we need to put, you know, if you notice, there is like a bunch of numbers here. So where did they come from? I'm going to explain in a second on the next slide, how we compute those numbers. But how we use those matrix is, I'll give you an example. Let's say we want to recommend, let's say we have this matrix, we computed all the numbers in the matrix. Then I want to make, say, recommendations to the first, for the first user. I can go 2 ways, right? I can say, okay, look, this is the first user. The first user is similar to this user and similar to this user and less similar to these guys. This is similarity weights. So what I can do is I can take the rankings of this guy, and these are the rankings from this guy. Here they are, here are those books, and multiply by the similarity to this guy. And then there is this guy I'm also similar to. So I take the similarity level times whatever this guy rated, whatever books he rated, and put here those ratings, all right? And so I get this combination, weighted combination of the ratings, and that calculates my predicted rating for the user, right? So I predict, just a sec, I predict that this user, this lady, will most likely like this book and will rate it 4.5, and this book and will rate it 3.0. This book and this book, she already rated, and that's why we don't compute for it. Please, what was your question?
Yes, I have a question about the similarity rate. How did we compute this?
This one, this number, this 0.75, right?
Yes.
Yeah, okay,
No,
yes.
No,
No, this one?
Yes, 0.7 and 0.6.
Right, so 0.7 is this 0.75, and this is this 0.63. It is a similarity in between this person and that person and that person. I was going to show you how you compute the, the numbers within this matrix on the next slide.
Okay.
Here, I just want to show how we use it, okay? So
Okay.
if you have this similarity matrix, then this is the way we use it. All right, now how do we compute it? Well, there is this quite simple way to do this. And here is a way. Let's say we want to build similarity. I'm showing actually here. Okay, hold on a second. There you go. Let's say I want to see how similar this user is with this user. I look at this matrix, and I'm looking at these two vectors. This is a vector, and this is a vector, right? Now, some of the the spaces are empty, so we ignore that. But some of them, overlap. Here overlap, and here overlap, right? So these are two vectors, and you can think about this user as being a vector in 1, 2, 3, 4, 5, 6-dimensional space. So these are two vectors, one vector and another vector. So if you look at them in this multidimensional space, this is one vector, that's another vector. What you can do is you can actually calculate angle between those vectors. To calculate angle, it's actually cosine of the angle. You use the sort of standard formula for the cosine of the angle between vectors, which is, will be vector A, this will be vector B. And so you find the dot product divided by the length of each vector. And that, what would go into that matrix, where is the matrix? That, the number that would go right here. Make sense? Or it's too scary?
A little bit.
A little bit. Okay, let me try one more time on a different example. Let's look at the similarity between two books. So a book, say this book and this book. I want to understand how similar they are. In order to do that, I will think about them as vectors. And look, when you have two vectors, and it's sort of conceptual thing, but it's very typical in information retrieval. So when you have two vectors, if the vector is pointing in the same direction, you think about them as being, identical, right? They point in the same direction. When they're orthogonal, they're pointing in different directions, so they are independent. And similarity between vectors measured by the angle, or often by the cosine of the angle between vectors. So that's what it is. It's a dot product in between one vector times another divided by the length of the vectors. And so you start thinking about those books as vectors, and these numbers are the coordinates of those vectors. And yes, they're not in 2 dimensions, they are in actually 6-dimensional space because there are 6 coordinates. Some of them missing, but some are present. And so we're ignoring those that are missing, and we just calculate, we just use those that are present. And so if this is vector A and this is vector B, I calculate, well, cosine is going to be equal to vector A, which is 5 times 3 plus 2 times 4. And I normalize it by the length of one vector, which is square root of, is going to be what, 4 squared plus 5 squared plus 2 squared, and the length of another vector. and that's going to be cosine, and that's going to be your similarity. And after I do this, so this is a book, and this is another book, right? So I calculate similarity between those two books. So this is a green and the red one. Then I go back to this matrix, and let's see where the green, and it's this book and this book. This is a similarity that I just calculated. All right, does it make more sense now?
Yes, thank you.
Okay, good. All right, guys, we're actually getting pretty short on time. I will probably skip this slide. I'll just mention that what I just discussed, what I just described to you is the sort of, very, very basic collaborative filtering. It's sort of where collaborative filtering, where recommender systems started in the year 2000. Now, amazing, but it was 20 years ago. Since then, there has been a lot of progress within the recommender system. There was a Netflix prize where Netflix paid $1 million to improve their recommender system quality by a few percent. And a lot of research has been recently done in recommender systems regarding this matrix type of approaches. And if you look at the matrix, right, the matrix we just saw before, the recommendation problem is really a problem of finding how to fill in those empty cells, right? Finding a ways to fill them in. And you can actually just take like average across rows or columns and use that as ratings. Or you can, use much more advanced algorithm like matrix factorization and other algorithms. I'm not going to talk about it today, but there are lots of ways you can try to fill in that matrix. And if you manage to fill that matrix, that's really a recommendation, because if you can predict, what does it mean to predict that this person will rank this book? Well, it means really to put here a number, right? If it is 5, here it's good rating, and if it is 1, it's bad rating. And you can also, if you think about offering products, the same way you can put their probability of purchase. So filling in the matrix is equivalent to building a recommender system. Okay, so we are almost done. There are a couple more practical things. One practical thing is, how do you actually measure the quality, right? Because as always, with any machine learning algorithms, we want to measure the quality. And if you remember with, for example, clustering, which is unsupervised learning, the problem with the usage of the clustering is that we cannot evaluate easily quality. And so we want to make sure if we have supervised learning setting, and this is a supervised learning setting, that we can evaluate quality. By the way, notice that recommending purchase, not purchase, it's really a classification problem. You have an user and you have an item, and the classifier has to decide purchase or not purchase. And a recommendation system, recommender, where you do ranking, right? Trying to recommend movies, trying to predict the ranking. It's really a regression problem. It's just, instead of in this problem, your sort of samples, not just users, it's a user and a movie. And together, for them, you want to predict the value. And that value, it's a regression problem. So recommender system is a supervised learning problem that can be either cast as a regression or as a classification, depending on sort of your flavor. And so you should be able to check the quality. And the way to do it is, as always with supervised learning, is to split the data into train and test set. Now, the only challenge here is that because we're kind of working in this world where we have, both users and items, you cannot just take that matrix and split it, cut out a bunch of users and, check for the users. So what you want to do is you want to take a few items. So you're not just selecting particular users as a train and particular users as a test. So or particular items as a train and particular items as a test. So you don't do it that way. What you do instead, you for each user or for some percentage of the users, you take some items that they purchased or some ranking that they did, and you hide them from the system. So you know them, but you hide them. And so you're splitting into train and test, not by users or by items, but for each user, you hide some items, some small number of items. And then that becomes the train and the test set. Okay?
Yes.
All right. Now, a couple more things. If we're setting this up as a ranking problem, as a regression, then the quality is measured by just RMSE, the same way as for any supervised learning, where this is a prediction, this is the actual, and that's it. If we set it up as purchase, not purchase, as a sort of binary problem, then we can measure it with our traditional confusion matrix. That's absolutely fine. And for the confusion matrix, you can calculate the true positive rate, false positive rate, etc. But there are a couple metrics that are traditional for information retrieval. We haven't discussed them before, but they are very common. They're called precision and recall. And here, how you build them from our confusion matrix. True positive, false positive, true positive, plus false negatives. And then there is a metric F1 score, which is a combination of those. Now, I want to briefly explain what precision and recall is in plain English. Because, looking at this TP, FP, even I have a hard time imagining what it is, but in fact, it has very simple meaning. So precision tells you the following. Out of those ranking let's say it's not ranking, it's purchasing, right? Out of those items you have predicted that the customer will purchase, how many he actually purchased? That's it. So it's how precise your prediction. So if everything you predicted he purchased, it's 100% precision is 1. If you predicted a bunch of items and the customer hasn't purchased any of them, your precision is 0. So it's a percentile of the actual purchase within your prediction. So this is your prediction. That's what actually has been purchased. The ratio is precision. And recall is the ability of pick up all the information, which is, again, this is what you predicted, and this is what he overall purchased. So if he purchased some items and you have not predicted that he will purchase it, your recall will be low. So recall is sort of coverage, if you wish, right? How well you cover all the items. Precision is usually the most important metric. It's really within your response, within your prediction, how much you got it right, how many items you got right? That's precision. And this one is, have you picked up everything that customer purchased or not? Or did you leave something behind? You said something, you said he's going to purchase. You didn't even predict that he will purchase those items. So those are 2 metrics. Now, to wrap it up, and we're running out of time, I'll take 2 more minutes of your time. So the recommender systems, we talked about the sort of so-called, first generation recommender system, which is this collaborative filtering, right? And as I said, there is also content-based and there was hybrid systems. Then there was a second generation, which is again, probably after 2000, people start working a lot about in various matrix factorization. And then there is a sort of new wave of recommender system that are currently based on deep learning and all kind of neural network analysis of the data. Sort of the last thing I want to show you is this. This is a screenshot from Amazon, which is explicitly differentiates in between association rules, remember those, and recommender systems. So When you think about association rules, this is items frequently bought together, right? This is a one transaction, and that's how it works. This is a frequently bought together items. And this is a clear recommendation, sort of user-based recommendation system. Customers who bought this item also bought that. And it's shown to you because the system believes that you're similar to these customers. So these association rules, this is the recommender system, okay? So that's how they work in real life. And I think the last slide is here. If you're interested in how, how those systems sort of deep inside architecture and all the details on how to implement both association rules and recommender system at scalable, this is a very good book. I believe, so Jeffrey Ullman, I think he's from Stanford. There is a new edition of this book with another professor. And Anand, he was, I think he was running the lab at the Walmart, Walmart labs. So they know really well how those things work. And we're done for today. The last announcement is actually, let me stop recording and